kind of the physical process of converting graphite into diamond, which was a pressure dependent process. And the other one looks at the boiling of water as a function of temperature. So we'll talk about the tools that we need to do this today and on Wednesday. I would recommend, if you want to tag along and follow along on Wednesday, to bring something that has Excel on it for Wednesday. There'll be some practice dealing with enthalpies and heat capacities and things like that, which are topics I'm introducing today. We'll deal with them practically on Wednesday. So bring something with Excel if you want to tag along. Otherwise, you can just pay attention to what I'm doing on the screen. Okay, so we've come up with this nice little function called enthalpy, which allows us to track how heat changes in the system for a process, a chemical or a physical process. And the one that we've been focusing on in particular in class the last couple of lectures has been phase transitions. And I want to stick with phase transitions for a little while. It will always be in the background because it's a really nice way to think about heat, something that we experience every day in our lives, or phase transitions. And they use enthalpy as a way for us to identify, as we'll see today, different types of phase transitions. And I don't mean liquid to gas, gas to solid, things like that. I don't mean as in that, but completely different behaviors and different types of phase transitions. They're completely separate from each other. So we're going to find that there's this type of phase transition that's like vaporization, solidification, and the ones that you're used to. Talk about what the definition of those are. And then we'll identify today a different type of phase transition that behaves completely different. That'll basically allow us to start talking about the classification of phase transitions, which will integrate into our discussion about enthalpy and entropy, and ultimately Gibbs free energy, which we'll get to very soon. So let's start probing phase transitions using heat. We'll think about what we can learn from them using heat as our guide. And so I just want to do, once again, I want to motivate ourselves with a little experiment. And I want to think about how do materials heat and cool themselves as they go through phase transitions. We're looking in particular between liquid and gas, right? The vaporization process of some gas or some liquid. The same thing applies to liquefaction, melting as well, or sublimation. The argument here applies. It's just that the states are different. In some senses, we'll learn the only difference between vaporization and solidification is that one involves a solid and one doesn't. So it doesn't really matter what we choose, but I think naturally boiling, the concept of boiling is something that we all appreciate. So let's look at boiling. Let's look at an experiment, a boiling experiment. Right, and we'll look at, it doesn't really matter what we boil. Maybe it's water, but in particular, I want to look at boiling CO2 liquid. There's a reason why I choose carbon dioxide here. Again, carbon dioxide liquid is kind of a strange thing. There's not carbon dioxide liquid at room pressure, right? Typically, the only ways that it exists in kind of the normal atmosphere is either solid or gas, but if you pressurize it enough, you can liquefy CO2, right? So we're not going to be in atmospheric pressure in this experiment, but some higher pressure. But just imagine that we can set a condition where we can have this equilibrium or coexistence between gas and liquid CO2. And at the end of the lecture, I'll show you a video of liquefied CO2. We'll actually look at this process. All right, and I'm going to do it two different ways with the same apparatus. All right, we're going to have a water bath or some temperature, and inside of that, we're going to put a flask. Or some sort of decanting, some sort of bottle that's cappable. All right, so we have a removable cap. Right, that can seal the environment or not. We can make a choice whether we want to keep it sealed or we want to keep it open to the atmosphere. This is a variable temperature heat bath, just like we'd use in lab. Sorry, heat bath. So you can set the temperature whatever you want, keep it constant. Right inside of this, we're going to have some coexistence of gas. We have our CO2 gas, and then we also have a liquid layer. And of course, we need one more piece of equipment. This is a class about heat and thermodynamics. We need a thermometer. So we have a thermometer that measures the internal temperature of the gas or the liquid. Okay, so it measures the content, right? Not the external temperature, but rather the contents. That'll be important in a second. So we can either have the cap removable or we can have it not. So if the cap is sealed, what is our conditions? Well, if the cap is sealed, the prep volume can't change. So the volume is fixed. So this is equal, this is a dV equals 0, no volume change. Conditions. This is called isochoric conditions. That's a little different than what we've been looking at in enthalpy, but the only difference between this and enthalpy is, or rather the conditions for enthalpy is that enthalpy has the cap open. So cap is open or removed. The volume of the gas can change, but the pressure is constant. And these are isobaric conditions. Very simple. Two different choices. Doesn't matter which one we pick. And what I'm going to do is I want to apply some heat using my bath to this mixture. And what I particularly want to do is I want to have some sort of calibration for my heat, all right? How much heat I put in. So what I'm going to do is instead of have a temperature set where it just turns on and off, I'm going to put a heater, a coil, if you will, below the bath, that instead of having a set temperature, you set the amount of energy it feeds in. So it's got a fixed amount of energy instead of a constant temperature. So I've got this heating coil. Right, that's radiating heat. Right, this is a heating coil that provides a constant amount of heat energy per second. Right. If you're down with your units, we have something that's providing a constant amount of joules per second, so it has a fixed wattage. And so this is a fixed watt heater or constant wattage heater. Right, which is just like the, I don't know if you guys have it, but I know some of you live in certain dorms that the heat likes to go out of your apartments and you have these little space heaters. Those space heaters always put out the same amount of heat. They're set to some amount of BTU, some wattage, and you turn them on and they deliver that much heat. Typically, they're about a kilowatt or 1,500 watts. And of course, the amount of heat it generates is constant, so it depends on the size of your room, how much gas you have to heat up, whether you notice it or not. But those heaters just provide a fixed amount of heat. All right, so what we can do now is monitor the temperature as a function of time. Turn the heat on and watch how our material heats up as a function of time, right? Because we're fixing we have a fixed amount of energy going in, so there's a fixed amount of heat. And so we can watch it as a function of time to see how the temperature changes. So now what we're going to do, as I said, was we're going to monitor temperature versus time. So we can make a plot of time versus temperature in some degrees, Kelvin or something like that, doesn't matter. Right. And let's say we start at 298.15, we start at room temperature at T equals 0. And the temperature is going to increase at some rate. Okay, it's going to have some. Now we're going to see that, in fact, it's not a straight line necessarily, but let's just assume it's a straight line, that the temperature increases linearly in time. We'll see eventually that that's not the case. But that will be have a linear increase of energy. Right, so the temperature of the water continues to heat. Right, and eventually we hit boiling, right? And boiling depends on the unit of pressure that we're at. So we'll just have a rather some boiling point. See the liquid heat at some rate. And then what happens next? Well, let's think a little bit about what happens when you say boil water for macaroni or something like that. Your water continually heats up, starts to boil, you get a nice rolling boil. Now, I know probably no one's ever done this before, but it's a nice test. You take a thermometer, right, you'll see the temperature of your water boil, or sorry, to start to increase. And then when it hits the boiling point for your atmospheric pressure, the temperature flattens. Temperature doesn't increase anymore. So while the system is boiling, the temperature is constant, doesn't fluctuate at all. So what we observe during boiling, we will say boiling takes a little bit of time. You know, boiling doesn't happen instantaneously. So during the period of boiling, the temperature is completely constant. And eventually you boil all the liquid off. If you guys have ever forgotten about your macaroni water, you just let it boil and it disappears. What happens? Well, then the pot starts to heat like crazy, right? The gas inside of your pot starts to heat, and your pot starts to increase to the energy or the heat, the temperature of your stove, and you have a fire or you burn something, or my wife yells at me, things like that. And the thing is because the temperature again starts to increase again. Once that water's all boiled and turned into gas, it now heats like a gas. And a gas heats much more rapidly per unit energy, input energy, than a liquid does. The gases heat very, very effectively, very quickly. And so what we see is the temperature skyrocket in the gas form. Okay, and it can continue on. So that's a really interesting plot. Right, first, what are some things that we notice by the way I've drawn this? Well, first of all, remember that the system is applying the same amount of energy at every point here. Okay, so the liquid is receiving just as much heat as the gas is. But the liquid increases more slowly in its temperature than the gas does. The gas increases rapidly. Okay, so we don't have to call this time, right? Because every moment of time, a specific amount of energy is input into the system from the coil. So what I could write at the bottom instead of time, this is also proportional to the input energy. Right? It's the same thing. Right? Time and energy are linearly related because we have a constant supply of heat. So what we see is that the liquid, as a function of the input energy, the temperature increases slowly. When it hits boiling, it doesn't increase at all. And then for the gas's temperature reacts much more violently to the input energy than the liquid does. All right, let's try to understand why that is today. Again, what I'm showing you here are just experimental results. This is just empirical. So let's go back and understand why that is. And let's make some notes about that, right? So what are the notes? Well, So some observations, just more technical ones than what I've just given you qualitatively, is one that the slope of the gas curve is larger than it is for the liquid, right? So what is the slope here? Well, the slope is the derivative of temperature with respect to the change in energy for the gas, right? That's the slope of that curve, that line. E, right? E is the x, t is the y, the x. And that's greater than dt dE of the liquid, which is greater than dt dE at boiling, which we observe to be 0. That's interesting. Maybe we can measure that. What is that number that we're measuring? That's the big observation. All right, so this technique of where we are looking at how the temperature changes as a function of time or some process that we're doing, in this case, in terms of input energy from our heat. We have a term for this kind of technique. This is what's called calorimetry. Calorimetry, which is the measurement of temperature changes with heat. Right. To go up into the instrument lab where the NMR is and the mass specs upstairs on the 3rd floor, there's that back wall. It has the NMR, the atomic absorption spectrometer, the flame spectrometer. In the back corner by the door that connects to the analytical lab is this little white box. It's got some Chinese text on it because it's a Chinese manufacturer. And it's a differential scanning calorimeter. This is Dr. Sun's calorimeter. What Dr. Sun's calorimeter does is exactly this. It has a fixed calibrated heat source. He puts some material in there, and he can monitor the way that, the way that the material absorbs that heat as a function of time, and identify, say, for instance, when it melts, when it boils, different types of physical properties of that material. And so you can buy instruments that do this, and in fact, in lab, starting this rotation, you guys will be doing a calorimetry experiment as well. So this is something you'll see in lab. So what can we learn from? Well, these are kind of weird slopes, right? Because we're not really used to T being the output of some function. Remember, we usually measure the energy as a function of temperature, whereas this is some function of temperature, that's some function of energy, T, right? This is a function T of E, or applied energy. So we're used to thinking about changes in energy with respect to changes in temperature. So the flip of that. Okay, so let's flip it over instead. So more convenient. Is we take 1 over the slope of these curves, which is dE dt. Right? And this is just a number, right? This is a slope. This is just a number. And we have a name for this. This is called the heat capacity. So every material has this special heat capacity. Just a number that associates in some sense, right? This is the ability, so the amount. And this is the CHEM argument or description of heat capacity is the amount of energy required to heat the sample by 1 degree Kelvin. Right, which is exactly 1 over what we were measuring. We were measuring how much energy it takes to raise the temperature by 1 degree. And that's exactly what the heat capacity is telling me. Right, so that's the CHEM definition, right? But what if, for instance, the heat capacity was not a number, but a function of temperature. Right. So what would that curve look like instead? Well, our calorimetry curve would instead have some curvature to it. Like this. And then it would boil. And then the gas may have some different behavior. Right? What if it's right? So what if, for instance, here, the heat capacity of the gas or the liquid is some function that is say a quadratic function of energy. Right? And maybe then for the gas, it's just a linear function in energy. Right? Then it's not really fair to say that the slope of that curve is the amount of energy it takes to heat the material 1 degree Kelvin, because the amount of energy it takes to heat the system by 1 degree Kelvin is different here than it is here. Right? The slopes are different. So if I were to draw a tangent to the curve here, right, the slope of this is 1 over the heat capacity. And then we put one here. Slope is the inverse of the heat capacity. Right? We have different heat capacities at different temperatures. Right? At higher temp, and from this and this curve, the heat capacity decreases for the liquid as T increases, or sorry, as E increases, or it says T increases. Sorry, E. E is our, right, as we put more energy and heat the system up, the heat capacity decreases. Okay, so really what the heat capacity tells you, rather in a more CHEM sense, the CHEM definition is that heat capacity measures the specific heat content of a material per unit Kelvin. Right? What does that mean? Imagine that molecules or material holds heat like a bunch of apples, stuff, right? And every time the temperature increases by 1 degree, that implies that the molecules have, in some sense, put whatever's in their hands, they've run out of space and they've stored it away. All right. So every time they store their handful of their bushel of whatever material they're picking out from called heat. Every time the temperature goes up, they store that away and then they start gaining more heat. And then eventually they run out of room and they put some more in, the temperature increases. Okay. And so the heat capacity tells you in some sense how much can the molecules absorb that heat before the average temperature, rather the average energy of the whole system increases by 1. So you can think about the average energy of the system as like the reservoir of energy available. And as you start to apply energy, the molecules hold on to that energy internally until they run out of it, and they have to instead increase the reservoir that's available, which increases the temperature. So the temperature kind of, in some sense, is like the fat content, the fatty heat content of the thermodynamic body. Really hot material people, and so what that means is that systems that have very high heat capacity, from that perspective, have very high heat metabolism, in the sense that they can consume the heat without having to store it and increase the temperature, the reservoir content. But something with a low heat capacity, right? They only have to eat 100 calories of heat before their weight increases by 1. Body starts to store it as fat. So you can kind of think of it that way, is that materials have different abilities to absorb that heat and store it without causing the random motions of the system, which is what the temperature measures, to increase. How much can they internally store? All right, and so what would that say about, let's go back to the curve that I drew before. What would that say about our heat capacities? Remember that the slope of these are the inverse of the heat capacity. Heat capacity is a change in energy Y with respect to X, temperature. These are the opposite. So the gas has a larger slope here, which means it has a lower heat capacity than the liquid. And then the liquid itself has a larger slope here, or sorry, lower slope here, a slower slope here, which means it has a larger heat capacity. Meaning that liquid CO2 can, in some sense, absorb more heat, metabolize more heat before its fat reservoir kicks up by 1 pound or 1 Kelvin. So we'll see by Wednesday why this is, why liquids in particular universally have a larger heat capacity than a gas. And as we'll see, solids have a higher heat capacity than liquids. We'll look at that very carefully in this class. Now, you might have some sense that that's the case. You think about different types of insulating material that you have, trying to insulate things from being hot or things keeping it hot or keeping it cold, right? Typically, gas exchange, right? Using a gaseous layer, just air, is not an effective heat insulator, right? Think about your coffee cup. You just get one of those cheap little ceramic crappy coffee cups, novelty coffee cups, low constant pressure. It's not very well insulated. And typically, those ceramic cups have a layer, a hollow layer in the inside of them from where there's an air gap. So the insulating material has air in it, and they tend to do very poorly at holding the heat of your coffee. That heat exchanges very rapidly with the outside air, and your coffee is only hot for about 5 minutes. But if you put it in your Stanley cup, that thing's hot for 12 hours. And why is that? Well, because it has a layer of aluminum, right? A metal which has high heat capacity, and also another layer of ceramic on the outside, high heat capacity. And typically there's some sort of insulating material in the middle as well, which has a high heat capacity. Okay, because it has a high heat capacity, that means it takes a lot of energy from the liquid to be transferred and increase the temperature of the Stanley or the exterior of your Stanley by 1 degree. So in some sense, it takes a lot of energy to heat your coffee up because it has a high heat capacity. The heat capacity of your Stanley mug is even higher. And so the opposite is also true, which means it takes a lot of output energy to raise the temperature of the exterior by 1 degree and therefore lower the temperature of the coffee. Okay, so you just think about the perspective of how energy flows, and heat capacity applies in both ways. I'm very familiar with this. I do a lot of things in a vacuum. One of the worst things, a really, really good heat capacitive material, is the vacuum. And that's for an opposite reason. Gas and liquid, it's easy to conduct heat through them. It's very hard to conduct heat through the vacuum. There's nothing to absorb that heat. So a vacuum insulation, for instance, is very, very, very effective as a heat absorber. But for the opposite reason, it's not that a vacuum has a high heat capacity. It's that there's nothing in the vacuum to absorb the heat. So there's no way for the heat to transfer. So that's why, for instance, the space shuttle or like the the ISS, they don't really have problems with heating and cooling. They don't have to have a constant HVAC run because the system is basically, it's impossible for it to radiate heat away because it's in the vacuum of space. So most of the heat is trapped inside the ISS, so it's not too hard to maintain decent living conditions in the ISS because there's no way to get rid of that heat that you put in there. So there's a sense of conductivity that you have to consider as well when you think about heat capacity. We're not worried about that here because we're not in the vacuum. We have materials that can exchange heat readily. Okay, so let's just be a little more careful of how we define heat capacity. Kind of just the nitty-gritty notational reason things about it. Kind of just keep ourselves in check with the rest of chemistry. I want to define the heat capacity specifically. There are two. I've mentioned two different containers, one with the cap off and one with the cap on. I haven't mentioned why I did that yet, but here's the reason why. Is that there's a difference in heat capacity between the two examples. I'll explain why that is. So heat capacity is measured in two ways. First, there's the constant volume heat capacity. Which says that the change in heat for a material with respect to the change in temperature, this is heat. We can't define enthalpy for constant volume. Remember, it's a constant pressure term. We call it heat instead. This is equal to, at some temperature T equals T star, is the heat capacity of the material evaluated at T star. Right, so this is the constant volume heat capacity. It's called C sub V. And then there's the constant pressure heat capacity. And constant pressure, we can use enthalpy. We define the heat capacity as the change in enthalpy with respect to the change in temperature, evaluated at some temperature. Rewrite this as Cp, constant pressure, evaluated at the special temperature T star. All right, there's a very simple, right? So what's the difference between these two? Well, there's only one difference between a sample at constant volume and a sample at constant pressure. A sample at constant volume does no work. It just heats up and the pressure increases, right? The volume can't change, so the system can't do any work. It just gets increasingly more and more compact, more and more crazy and chaotic at that high temperature. Constant volume. At constant pressure, the gas can, right? A gas can do some work, right? Because imagine if you have a boiling process. Let's go back to the first slide really quickly. I think it's nice with the picture, right? Imagine you just had liquid, okay, and you measured the work being done by that liquid, which is very little, right? The work that the liquid only needs to do is to fill its space. And you hit boiling, right? At boiling, you start to build up instantaneously a pressure of your gas. And so if we just like took a quick snapshot, right, at boiling, we have this layer of CO2 gas that's expanding. Right? If it's constant pressure, that means the cap is open. Right? So some of that energy being used for boiling or to heat the system has to be used to allow the gas to escape and to exchange with the atmosphere. So there's some work being involved in a constant pressure system. And we saw that when we talked about enthalpy a couple weeks ago. We noticed that for a condensed phase process where we looked at calcite and heat, or the other type, aragonite, there's very little work difference being done, right? There's very little work done in order to move things around. It's all chemical change. But in the case of liquefying, taking liquid H2O and converting it to H2 and O2 gas, or vice versa, we have a big change in work because you're converting between a liquid to a gas. And of course, the gas expands and compresses freely. And so as you start to build up pressure in your constant pressure device, you have that expansion happening from the boiling. And in order for that to equilibrate with the atmosphere, some work has to be done, right? You have to shuffle that gas out and bring the gas in. So that means that the heat capacity at constant pressure is different than the heat capacity at constant volume, because in some sense there's an additional motion that the system has to do, additional sink of energy in the constant pressure piece. So they're different by a small amount. And what is that small amount? Well, we can kind of think from our discussion over the past few weeks, is that when you're at thermal equilibrium and you have a motion that appears in your system, how much heat energy is applied to it? Well, it's around the factor of RT, function of R. Heat capacity, or R, the gas constant, tells you something about the heat content at some temperature. And so once you do the math, you find that these are interrelated to each other by one factor of Avogadro's number times the number of moles. Right? So this is just the difference in the heat capacity of that expansion motion. Right? So all this is saying is that the heat capacity at constant pressure is larger by one motion's worth of heat content. Right? This also tells you something about the units. Again, we know what the units are. Heat and enthalpy are joules. T is temperature, right? Kelvin. So these units are joules per mole Kelvin, right? Which are the same units as R. Right. So this is another way to interpret R, is that R tells you the average heat capacity of a single motion in a gas. Right? This is just the expansion motion that the CV doesn't, the constant volume system doesn't have. Just one factor of R. Okay, and so we don't really have to, that's a small difference, especially if the heat capacities are large. We're at 1 mole, and R might not be that big. But it's something to consider. Okay, so let's see what we can do with this. What can we learn from the heat capacity of our system? So let's return back to our example of boiling. Right, we can calculate an enthalpy of vaporization for this process at room temperature. Right, and how do we do that? Well, all we have to do is calculate take the enthalpy of formation for CO2 gas and subtract it from the enthalpy of formation for CO2 liquid. Right, we went through enthalpies of formation, looked at them on NIST and ATCT. Let's go ahead and figure those out. Notice that these in particular, I haven't really specified this. These are at standard conditions. That's what the little dot means, the little circle means. Which of course is 298.15 Kelvin. And pressure equals 1 bar, right? STP. Anytime you see that little dot, little circle, when I talk about enthalpy or entropy or Gibbs free energy, just remember that means standard conditions. I'll remind you of this over and over again. So let's go look online. I don't know these numbers off the top of my head, neither should you. But someone does. Okay, well, I have the A delta HF for the gas. I don't have it for the liquid. Oh, actually, it's right here. There's the liquid. This is aqueous. Right. We'll just use the aqueous number as our liquid form. It doesn't really matter too much. Let me see if those are any different. Another place we can look. Let's just look one more time. On NIST. Not on there either. So the enthalpy of formation for the gas is 393.477 kilojoules per mole. And then we need to calculate it for the liquid, and that's going to be a negative number. I don't have the liquid number, but we can use the aqueous one. That's good enough for us. Minus 412.868 kilojoules per mole. All right, so this should give us a nice positive number, as it should. Boiling is always an endothermic process because you have to break the internal interactions between all the CO2 molecules in the liquid. This should be a positive number. Let me just go ahead and calculate it for you. So it's about 19.4 kilojoules per mole. Okay, so at room temperature, if we have liquid CO2, we have to put in approximately, all things being equal, about 20 kilojoules per mole to get it to boil at room temperature. All right, so I like to think about these numbers graphically. I think about enthalpies and differences in enthalpy. It's nice to think about things kind of all on the same plot. So let me kind of show you my strategy to think about this. So what I'm going to do, I'm going to draw a little plot. Not really a real plot, just kind of what I'm going to do is plot on the y-axis the enthalpy change of whatever material I'm looking at. And I'm going to put two entries on the x-axis for my two reactants in my products. So I'm going to put here the enthalpy of CO2 liquid and the enthalpy of CO2 gas here. All right, so the liquid is at minus 412. Let's do minus 413. And what I'm going to do is I'm going to put a little line here, minus 414 for the liquid, and then minus 393 for the gas. Okay, so these are the enthalpies of my two states, of my products and my reactants, right? And the difference in enthalpy is just the vertical distance between the two, right? So I can just draw a little line here like this, and this is my vaporization enthalpy at room temperature. All right, we'll do lots of little coordinate diagrams like this in class. I think they're a really great way to think about energy. Now what we're going to do is we're going to take our coexistence, our liquid and our gas, and heat them up. Right? And what I'm interested in is how does the vaporization enthalpy change as a function of temperature? So what does HVAP look like at temperatures other than room temperature? Well, we have an equation for that. We have the equation that the derivative of the change in enthalpy with respect to the change in temperature, or where's the change in enthalpy? Let me get rid of the delta H. That's confusing. We'll use that in a second. Is equal to the heat capacity, constant temperature, at constant pressure. All right, we'll do everything at constant pressure today. What can I do with this? Well, I can multiply both sides by dt. Multiply both sides by dt. Now, most mathematicians would cry by me doing this, but it works for our math here. All right, we're going to assume dt is not zero here. Otherwise, this doesn't work. And so we have that the change in enthalpy is equal to the heat capacity times the change in temperature. All right, so what I want to now think about is how much is the enthalpy change as I change the temperature by some fixed amount from initial to final, right? Some macroscopic change in my temperature. Well, in order to calculate the accumulated change of my enthalpy as I accumulate change in temperature, right? I have two derivatives, a differential, and I want to accumulate differentials. That means I just have to take an integral both sides. So I need to integrate both sides. Right? And I'm going to integrate from, say, the initial temperature, which is room temperature, to my final temperature. So I have the integral from initial to final of dH. And that's going to be the integral from the initial temperature to the final temperature of the heat capacity times the change in temperature. Now, if heat capacity is just a number, meaning it's the same value at every temperature, I can just remove Cp. So I have there's two limits here I have to choose from. One is I assume heat capacity is a number and doesn't change, and one that it's temperature dependent. So we have to consider both cases. So let's do the easy case. This is the CHEM case where Cp is T independent. This means that the change in enthalpy, that's the enthalpy at the final temperature minus the enthalpy at standard conditions, is equal to the heat capacity times the final temperature minus 298.15. Right? You've used this equation before in Gen Chem. This is exactly the same equation, just using enthalpies instead. The heating equation, right? That the heat required to increase the temperature by X degrees, delta T, is N times the heat capacity. It's the same equation from Gen Chem. But what if the heat capacity is not temperature dependent or independent? What if it's temperature dependent? Right. Well, then Cp is a function of temperature. Right. So then we have to define the function. It's going to be some number times T squared plus T. I don't know what the function looks like. It'd be a polynomial. I have to integrate that polynomial. Right. So that integral, I don't know what it's going to look like, but we'll find out. It's going to look like the integral from Ti to Tf of just some function of T. Right. Maybe it's AT cubed plus BT squared plus CT plus dot 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 dt. Right. Just some function. So this is an experimentally determined function. Right, we'll look at that. We'll see how important that is. And actually the homework really, really drives this point home, or whether this is a reasonable assumption. Heat capacity is temperature independent. So we might have some fun, right? So regardless, right, just some math. And in fact, this is the math we'll look at next class. That's why when we bring Excel, we'll actually work these out. I'll show you how to get this data, heat capacities, and actually calculate things very precisely. Do it all together, and you'll practice it on the homework. But the important thing to note is that the enthalpy of each of these materials, the liquid and the gas, right, are going to increase. The heat capacity is positive. They're going to increase linearly of change in temperature. The enthalpies are going to change as Cp times T, right? They're going to be those straight lines. So let's go look up the constant temperature heat capacities for CO2 liquid and CO2 gas. So the heat capacity of the liquid at room temperature, there should be a circle. Just got to pull it up. Is 37 0.2 joules per Kelvin mole. And for the gas, I'll pull it up for you right now. Hold on, I don't like the values it's giving me. Just a sec, sorry. Oh, okay, great. All right, this number's wrong. So it's a hard number to find. It's about 100 joules per Kelvin mole. And then here it's about 54 joules per Kelvin. Okay. These are rough. All right, we'll calculate it more precisely later. So again, the liquid has roughly temperature about 2 times as much heat capacity, right? It can hold 2 times as much energy per unit temperature as the gas, as you expect, right? Liquids have, right, as we'll see, they have more ability to absorb energy. We know that empirically, and we'll look microscopically at that. But what does that mean? Well, that means that the enthalpy of the gas is going to increase more slowly as a function of delta T than the liquid. And so this value is going to, right, this bar right here is going to increase in value faster than this one. Right? So if I increase the temperature by some amount, right? So if we go from 298 to some new temperature, let's say, for instance, it increases to there, delta T, delta T, and now we're at this new point here. Well, we know that the liquid, the gas side, is only going to increase half as much. We'll say that's roughly half. Right, so this is Cp delta T for the gas. Right? It's a smaller number. Now, what's the difference between the two? The enthalpy of vaporization now is the difference between this point and this point, right? And that's much smaller. Right, so as we increase the temperature, the required heat to boil our carbon dioxide has decreased. Now that should make sense, right? We've increased the amount of heat content in our system. There's more energy to use. So not surprisingly, what this means is that there's, in some sense, excess energy in the liquid that can now be used to convert into the gas. It has more in the reservoir to do this energetically costly process. So not surprisingly, the required amount of energy you need to put into the system to facilitate boiling, which is this gap right here, decreases. But notice that eventually they're going to win out, right? Eventually there's going to get to a point where they're equal to each other. Now that's a very strange concept, because what we've just described about liquids and gases is that, again, the behavior I showed on the first page is completely universal. Any liquid that you take that you put it boiling at constant pressure, it stops heating. Go try it yourself in your kitchen. It just stops heating, stays at 212. So you run out of liquid and then the material skyrockets in temperature. So what this is saying, right, what's doing here, all of that heat that you're applying from the coil into the system right here, into the material, is being used. All of that heat is being used to facilitate boiling. So none of the input heat at the boiling point is being used to heat the material. It's being used to boil, because that boiling costs energy, right? It costs an input. So 100% boiling in some sense is a 100% efficient process. In the sense that if the system is able to boil, it will, and it will use all excess energy to facilitate that boil. But now what we've noticed here is that there's some strange behavior. At some temperature, the two materials, the gas and the liquid, they reach some enthalpy difference that's negligible, might even be zero. Now that means that in some sense that it requires no heat to boil the liquid and to break the internal molecular bonds, the intermolecular bonds, dipole-dipole interactions kind of thing. It takes no energy to do that to make the gas. Right? That's very strange. How can that be? How can you have a liquid that in some sense requires no energy to convert to a gas? As if they're the same thing. Let's think about that a little bit. Therefore, there must exist a temperature where the enthalpy of vaporization is zero. Now, where is that? Where does it happen for CO2? Well, we have a really easy way to calculate that. We want to show the temperature where the enthalpy of formation of, sorry, CO2, not H2O, is equal to the enthalpy of formation of the liquid. Right? This is another way to look at it, right? Remember, the enthalpy of vaporization is just the difference. So it's where the two are equal. This also means in some sense that the liquid and the gas have the same stability at this point. Let's keep that in mind. By this definition, gas and liquid have same thermodynamic stability. They have the same amount of heat, same amount of stability, no energy difference. Right? That's very different than at room temperature, where there's a very distinct difference in energy or stability between the liquid and the gas. Now we're at some point where they're exactly the same. So where is this temperature? Well, let's just roughly calculate it. Right, so let's assume that the heat capacity is temperature independent. Right, just to do the calculation easily, you'll look at temperature dependence in your homework, and we'll work on that next class. And so the equation we want to solve is the enthalpy. I'm just going to write the enthalpy of formation of the gas at constant temperature plus the heat capacity of the gas times delta T is equal to the enthalpy of formation of the liquid at standard 10 conditions plus the heat capacity of the liquid, delta T. Remember, each one increases. We just have to find where they're equal to each other. Well, we have all the values for this. So the gas is minus 393. And I'm just going to do it roughly, not precisely. 393 kilojoules per mole. The heat capacity of the gas is 54 joules per Kelvin mole. We need to convert that into kilojoules. So that's 0.054 kilojoules per mole Kelvin times delta T. And, oh, sorry, let me erase that, which delta T is the temperature, the final temperature where they're equal, minus 298.15 Kelvin. Right, and this is equal to the enthalpy of the liquid, which is somewhere here, minus 413. Plus the heat capacity of the gas, which is much smaller, or sorry, the liquid, which is 100.1 kilojoules per mole Kelvin, times T minus 298.15. Okay, so all we have to do is solve for T here. Right, just a little bit of algebra. Let me show you how I do this. I pull up Wolfram Alpha and just type it in and crunch it. That's 0.393, 0.054 times x minus 298.15. I just prefer x than t. We all know x minus 413 plus 0.1 times x minus 298.5. And T here is 732 Kelvin. So if we theoretically at 1 bar, and this assumes the pressure is 1 bar, if we have a sample of CO2 liquid at 1 bar, we can heat it to 730 Kelvin. And suddenly we're at this point where there is no heat change between the gas and the liquid. There's the same stability. Strange concept. It's even weirder than that. Here's something else you see. We observe, if we measure the densities of the gas in the liquid, now, why would we want to do that? Well, remember that density, if we defined it in terms of moles, molar density which is the number of moles per liter, right? So you can think of that as molarity. That's all molarity is molar density. Then the density, which is proportional, of course, to the density times the molar mass. We have to delete the molar mass out. That the molar density is equal to 1 over the molar volume, right? Liters per mole, right? And this is a measurement of the PV work done by the system. Right? Why would we want to do that? Well, remember that enthalpy is everything but the PV work. And what we showed is that this special temperature, the heat content, the heat stability of the material, the heat content of the material as a gas is the same as the liquid. Now, what about the PV part of it? The other part of it isn't controlled by the enthalpy. There's an additional term which has to do with the space that the system fills. That's the PV part. And the molar volume or the density measures that. Right? So all I want to say is that at this special temperature, the heat content of liquid is equal to the gas, right? Is that also true for the PV work? Right? Right. So if we take H plus PV, this is the total energy of the system. Right? And so if both are true, we could say that the energy of the gas and the energy of the liquid are the same. Right? Which means that for far we can tell they're the same stuff. Right? They have the same heat content, they have the same PV, therefore they have the same total internal energy, they have the same material, right? They're CO2. Are they any different than each other? There's no other way to measure it. They're all the same from the observables that we have for material, which are thermodynamic variables. That's density or volume, heat content, entropy, and moles. None of these have changed at this point. We have the same number of moles as we've always had. The volumes, as we'll see, are the same. And the heat content, the enthalpies is the same. The entropy is the same. Therefore, it's the same material. And that's in fact exactly what we see if we look as a function of temperature and the molar density of the material as a function of temperature. And I plot this special number, this special temperature, which we call TF. What we see is that the liquid density decreases as it approaches this temperature. And the gas, which of course has a less density than the liquid by definition, increases at this temperature and meets the liquid at the same point. So at this special point, the liquid is the same as the gas. So what do we have at this special temperature? These are both true. We have H liquid is equal to H gas. And we have the density of the liquid is equal to the density of the gas. Right. This is called, this temperature, the special temperature right here is called the critical temperature. And every material has it. All pure materials have a critical temperature. Right? Which all that means is that there's some special temperature where the enthalpy of the liquid and the gas and the density of the liquid and the gas become one and the same. And so what do we see at this point? Well, we see a liquid and we see a gas, right? So we have two phases here. And then outside of that, the densities are the same. And so out here we have one phase. There's no demarcation. The difference between a liquid and a gas ceases to exist after this temperature. Because here there's a difference in enthalpy. They have different stabilities. Here they become degenerate, which means they have the same energy, same state. And then after that, there is only one state left. No way to distinguish between the two. So we have this new phase transition, right? We have a phase transition that goes between these two. That's the one you guys know and love, or know about at the very least. Right? This is vaporization. Right? And then there's this phase transition across this barrier between two phases and one phase. This is called the critical transition. So we have a vapor transition and a critical transition. Vapor transition requires energy, and it transitions between two distinct states of different density and energy. And then we have this critical transition that takes a system that's initially of two states and transitions into one that's one. We call this liquid, this fluid on the outside, it's neither a gas nor a liquid, it's somewhere in between. This is what's called a supercritical fluid. So we call this region where they're the same, or the liquid ceases to exist, as a supercritical region. Every material has this point. There is some, right, because of the heat capacity difference between the liquid and the gas, there's some temperature where the two curves meet, or the two enthalpies meet. And at this point is where the distinction between liquid and gas disappears forever. Any point past that in heat and entropy, there is no distinction between the two. So what we would expect is that if we take our CO2 and we put it in this liquid gas co-equilibrium, that if we heat it up or pressurize it, we set conditions right, we should see the phase boundary disappear. We no longer have gas and liquid, but we just have one fluid. In fact, this is exactly what you see. I'm going to let Nile Red show us out. Please don't judge me for my recommendations. Anyone watch Caleb Hammer? He's like the Jerry Springer of YouTube now. All right, so this is a nice video from Nile. I don't have the audio on, but you don't need the audio, right? So he's got some dry ice, some solid CO2 here. And what he's going to do is he's going to put it in a constant volume container, right? So he's going to do a CV heating instead of a CP heating. Much easier to do the CP. Right, so he's got this sealed container here of CO2, and he's going to heat it up at 10x speed. You'll see again it melts. The pressure is starting to build inside of this. The temperature is rising, the pressure is rising. There's a clear meniscus, meaning there's two layers here, gas and liquid. All right, then he'll hit that special temperature and watch what happens to the meniscus. It boils, there's a small murkiness, and then suddenly there's only one phase. If he continues to heat and pressurize the system, it will continue being one phase. And then suddenly, once you start to cool it again, which he's doing right here physically, he brings it back over this level where the enthalpy now becomes non-zero. You get that murkiness again, and you return it back to the two-phase limit. This is the critical transition. The reason why we show it for CO2 is because it happens to be really easy to do. If you vary the pressure, you vary the temperature, you can do it in like 30 Celsius. It's not hard to do for CO2. You have to have the pressure higher for it. But this is a new type of phase transition. It's a phase transition that, again, the phases are very clearly changing. We're going from a system of two densities to one of one. That's a phase transition. But no heat is exchanged. And one of the things I want you to notice, let's just look at it one more time. What happens when you boil? When you boil, that the liquid progressively boils, right? You slowly lose liquid. It doesn't all suddenly boil and vaporize. When you hit that limit, you have to continue to put heat into it to drive the liquid off and convert to gas. But here, he hits the temperature at which it boils, if you will, and it all goes immediately into one phase. So there's different physics going on here. This process takes time. Freezing takes time, right? Your ice cubes in your freezer don't freeze immediately into one piece, right? They take some time to nucleate and grow and slowly adapt the water into the solid phase. It takes time and energy, right? Or it doesn't take instantaneous to boil the water. These take some time. And that's because, again, you're feeding in heat to process this. Constantly having to drive the system with heat to boil it or to freeze it or to melt it rather. But here, there's no energy change. System doesn't have to do anything. Just some sense it's just magically has smoothly left the regime of two phases and gone into one. And that happens instantaneous. It doesn't take any time. There's no nucleation event, no boiling event. It's just a smooth change without any drama whatsoever, except for that murkiness. We'll talk about that murkiness next class. So it's a very discrete, the critical transition is by definition completely different than the vaporization transition. They're both phase transitions, but they do not have physics in common with each other than that they are a phase transition. So what we have to do is classify that, right? We have two different types of phase transitions in chemistry. And one of them you've heard of, and one of you understand, the other one you don't. So what we're going to have to do is further classify these and understand why this is different than this one. And then the next question you're probably going to have is, what are some other examples of critical transitions? And they're, again, less obvious than boiling and melting and solidification. Those are all really obvious. But what kind of other things have this type of behavior, like the critical transition? As we'll find out, magnetism. It's something in chemistry that has this. Another thing, you see these kinds of transitions occur in other types of behavior. A critical transition can be shown to be the reason why I-95 goes from smooth flow to gridlock almost instantaneously without any significant input. The second order phase transition that occurs instantaneously across the entire traffic chain. All right, so we'll look at that more carefully over the next couple of lectures and start to think a little bit more about this. All right, have a good one, guys.
I thought I thought you were saying. I need inside of it, you go to my closet. I've never done the grade or the just.